Now we want to find the kinetic energy of a ring that runs between 12 centimeters and 12.1 centimeters from the center of a rotating disk of radius 20 centimeters, a fairly big disk, and mass 4 kilograms. So we want a ring about this big around and quite thin, just a millimeter thick, out of that ring, and we want to find its kinetic energy if this whole disk is rotating at 5 radians per second, and 5 radians per second being the best part of a cycle per second, about this fast. Okay, so what's the kinetic energy of the mass just in that one little ring? Okay, to calculate the mass of the ring, we probably want to first find its area. Okay, its area is just going to be, pi times its outer diameter squared, which is the radius out to the 12.1 centimeter distance, the area of the 12.1 centimeter disk, and we subtract off the area of a 12 centimeter disk, which would leave us the 0.1 centimeter ring between 12 and 12.1 centimeters. So those areas are pi times 12.1 centimeters quantity squared, and pi times quantity 12 centimeters quantity squared. Now we could factor out the pi and the centimeter squared that's going to come out of squaring these. We get pi times 12.1 squared minus 12 squared centimeters squared. Now we use brute force and calculate all that, but of course this is a difference of 2 squares, so the result is just going to be the sum of these numbers, 12.1 plus 12, times the difference, which is 0.1. 12.1 and 12 is 24.1, and we multiply that by 0.1, we get 2.41 times pi centimeters squared, and we never had to touch a calculator. Okay, the area of the entire disk, of course, is pi times the square of 20 centimeters, 400 pi square centimeters. Now, if we compare the area of the ring to the area of the disk, we find it's in the ratio 2.41 to 400 of the area, or 0.006 of the area of the disk. And if the mass is uniformly distributed with respect to area, then we would expect the ring mass to be 0.006 of the 4 kilograms, or 0.024 kilograms. Now, we could also have calculated the mass per unit area for the entire disk. We could have divided our 4 kilograms by 400 pi centimeters squared. We could have gotten a number. We could have gotten a good approximation. And then we could have multiplied that by the 2.41 pi square centimeters in that ring. But we should understand it both ways. Okay. Now, the kinetic energy of that mass is 1/2 the mass times the square of its velocity. What's its velocity? Well, we know that this ring is rotating at 5 radians per second, so its velocity is approximately equal to the velocity of a point 12 centimeters from the center. Now, somebody in class said, well, why wouldn't we use 12.05 centimeters, which would be halfway between the 12 and the 12.1, and that would have been fine as well. We're just trying to get a good approximation here. For the small thickness of that ring, it's not going to make a whole lot of difference, and we're getting a nice round number here, so we're going to use this. I'll also comment, and I did in class, that even if you go to the 12.05 centimeter radius, you still have more of the ring outside 12.5 centimeters than you have inside 12 centimeters. That's not the center of the ring for the purpose of this calculation. And then what do you mean if by the center of the ring when you're actually squaring that velocity? It gets kind of complicated. So we just bypass all that and make this simple approximation. And what we do in the next problem, we're going to be taking limits and getting integrals and so forth, and we're going to be talking about rings whose thickness shrinks down to 0 in any case, so it doesn't matter really as if that happens where between the 2 radii you use your sample point, you choose your sample point. It's going to all squeeze out in the limit anyway. Okay, well, so we're going to use this approximation, and then we use that to calculate the kinetic energy. We have 0.024 kilograms moving at approximately 60 centimeters per second. Now, some of that mass is moving a little faster than 60 centimeters per second. At 12.1 centimeters, you're going to have 60.5 centimeters per second. And you got some mass out close to the 12.1 centimeter distance. Makes a difference, but not a big one. So for the purposes of this question again, we're going to say the kinetic energy is just this, which I believe comes out 0.044 joules. I think it's 0.0436 or something like that. 0.436. And I'm not sure about that. Anyhow, 0.044 joules. Okay. Now the next problem we go on to talk about a ring, but well, actually let's include that because that still applies to this particular disk. Between radius r and r plus delta r, how much mass do we have? How much kinetic energy do we have? Well, the ring area in this case is pi times r plus delta r quantity squared minus r squared. I got those backwards, and you can see how that works. Same thing we did here. And then if we simplify that, we get pi times 2r delta r plus the square of delta r. Now, if delta r is small, then delta r squared is tiny, and we're going to ignore it. And we just get pi times 2r delta r for the area of the ring, and the mass of the ring will then be 2r delta r divided by 400. Of course, we get 2 pi r delta r up here. We get 400 pi down here, so I've already divided out the pi. But we then get r delta r over 200. The velocity is r times 5 radians per second. Again, we could have used r plus delta r here. We could have used r plus 1/2 delta r. But if delta r is a small quantity, it's going to approach 0. We don't have to worry about that. So here's our velocity. And what's our kinetic energy? Well, it's 1/2 mv squared. It's going to be 1/2 of this times the square of this. And you can work that out easily enough. In the next problem, we go on and actually do a symbolic calculation for the kinetic energy of the whole disk.